Hello and welcome to seminar number 13. Today we are going to talk about transactinides. And what are transactinides? History of a few, synthesis and half-life, and is there chemistry being done with transactinides? So let's get started. This is the periodic table. And if we look at the literature, most say that these are the transactinides because they come after the actinides. However, some might say that these also belong to the transactinides because they are not created in a Breeder reaction. They require a particle accelerator to be synthesized because Einsteinium-256 is the last element to do beta-minus decay in order to form the fermium-256, and Mendelevium is not possible in this process, so you need a particle accelerator to form Mendelevium and Nobelium. So some say it started with Mendelevium. Mendelevium was of course named after Dmitry Mendeleev, the father of the periodic table, and it was done via an alpha-N reaction on Einsteinium-253, which is quite remarkable because normally your target is not Einsteinium. Einsteinium is really unstable, and normally you would want your target to be not heavier than californium. Some will use curium, some will use californium, but Einsteinium is really unsuited for a target. I think they used like 3 billion atoms of Einsteinium or something like that. And it worked apparently, and Mendelevium was created. And as we can see here on this periodic table, this states the year of discovery from these elements. This will be quite important later. So the concept of transactinides or transactinoids was introduced by Glenn T. Seaborg in 1944. And the first real transactinide is Rutherfordium in my opinion. It was created via having a curium target bombarded with oxygen-18 projectiles and doing a oxygen-18 5N reaction. Rutherfordium-261 was created with a half-life of about 70 seconds. But what you want to remember is that the discovery of element number 104, Rutherfordium now, and element number 109 was during the Cold War. And during the Cold War, the different countries couldn't agree for the life of them not on a uniform name for these elements. Because of course, every nation wanted to have this or that element named after them and stuff like that. So, for example, element number 104, Rutherfordium, the scientists at Berkeley National Lab wanted to call it Rutherfordium. The scientists at Dubna wanted to call it Kurtachovium. And UPAC made the suggestion of naming element number 106 Rutherfordium. But Berkeley said no because they wanted to call it after Glenn T. Seaborg. So that's Seaborgium, and every other scientist that wasn't in either of those parties just went with element number 104 and they just named it element number 104, or in German was Element Nummer 104. There's another interesting story about naming different transactinides. So now we know how Rutherfordium came to be and the whole fight of naming this element, but also Darmstadium had a really interesting naming history. It first had the name Eka Platinum, which was called from Mendelevium because, well, it was below platinum, and UPAC also had their name, and the Russians wanted to call it Berkelium after Henri Becquerel, and the Americans wanted to call it Hanium after Otto Hahn. And of course, as you can read out of the name, Darmstadium, it is named after Darmstadt. It's a city in Germany. And the GSE in Darmstadt wanted to call it Wixhausium because it's a suburb of Darmstadt, and this was where this element was created, and they wanted to call it after this suburb name. Why is that a funny name? Because you can't name that in Germany because the German word Wichsen means to jerk off. And they kind of agreed that this was a very unsuitable name for such an element. So they did not call it Wixhausium, but they called it after the bigger city, Darmstadt. So official naming was Darmstadium in 2003. Okay, how do we synthesize these elements? First of all, you want your target to be californium at most, Einsteinium if you're really pushing it. The synthesis of Mendelevium was with Einsteinium and alphas, but most of the time you would want californium because it's element number 98, so it's a GG nucleus with 2.6 years of half-life. Very neutron-rich isotope 252 californium, and GG nucleus are quite stable, and depending on what element you would want to create, for example, if you want to create francium, you would use a gold target, but also lead and bismuth are okay. Bismuth is okay as it's quite light, but if you want to have a really heavy target, you would want this target to be quite stable, neutron-rich, and preferably a GG nucleus. If it's necessary, you can have the target uneven, so you can have americium targets, but what you don't want is the projectile to be uneven. So the projectile needs to be as neutron-rich as possible, preferred to be a double magic nucleus, but GG is pretty much mandatory. Otherwise, this reaction probably won't work. So we have oxygen 18 or calcium 40 or calcium 48. You know, these really well-known projectiles, or carbon 14 if you want it. But these projectiles have to be a GG nucleus and neutron rich. So of course you would want calcium 48 rather than calcium 40 because calcium 48 has a higher neutron axis. But of course separating calcium from calcium is really tedious as there are no gaseous compound of calcium known. Is it possible to do chemistry with super heavy elements? Yes, there is chemistry from rutherfordium, dubnium, seaborgium, and borium. The hassium also, and this is the list of all the experiments that have been done with these elements. And as you can see here, you can even have aqueous chemistry, so rutherfordium chemistry in aqueous solution, most likely in hydrofluoric acid and stuff like that. But with everything else, and after that, these elements are created under such high heat from this target being irradiated with heavy ions that you can't have aqueous chemistry, so you will have gas phase chemistry. But it's possible. And now onto some spicy stuff. We know how organesson was made. Organesson was made by having a californium target and it being irradiated with calcium 48 projectiles. But of course, you can't go heavier than californium, and now you have to switch the target and you have to have it as a GG nucleus, so you can't use scandium because scandium is directly next to calcium, but you will have titanium. And for now at the GSI in Darmstadt, experiments on the synthesis of element number 119, 120 with a titanium projectile was titanium 50 were unsuccessful. Anything past element number 121 are so-called superactinides. This name was also suggested by Glenn T. Seaborg, and it's interesting for chemists because there should be the first G electrons introduced. However, as we can see from other lanthanides, they don't quite obey this rule. So it could be that element number 121 does not have any G electrons, as we can see from thorium, for example. And if you want to start learning a bit more about the history and chemistry done with super heavy elements, I would highly recommend to you to read Mein Lieblingselement Rutherfordium. It was written by my professor who did Rutherfordium chemistry. Of course, it was written in German, but might be a very advanced Duolingo lesson, right? It was this research here. So hexafluorido Rutherfordium complexes by Strupp et al. Really interesting story. I would highly recommend you go read that if you understand German. If not, go run it through ChatGPT or something like that. With that being said, thank you for your attention and goodbye.